Our out-of-this-world lead is way out of this world, 390 light-years away to be precise. To set 1 light-year is the same as 6 trillion miles. Man's insatiable interest has driven us to a vacillating exposure that transcends the actual epitome of time. In a shocking new development, the astounding James Webb Space Telescope has, as of late, gotten an enchanting glance at a glorious design beginning before the presentation of stars, demonstrating an object older than the universe itself. The consequences of this disclosure are massive, persuading analysts to truly seek answers to this bewildering problem. Could our perception of the Big Bang be flawed? What forces contributed to the arrangement of this perplexing plan, going back an astonishing 13.8 billion years? We should dive into the subtleties across the immense, endless region. The James Webb Space Telescope has emerged as a stunning space observatory, capturing the vast point of view of stars and the universe, and transmitting its astonishing insights to Earth. In fact, it unveiled a puzzling showcase, a 13.8 billion-year-old heavenly development testing the very underpinnings of our cosmological understanding. Through this surprising mechanical miracle, we find ourselves confronted with a huge astronomical mystery, eccentrically woven into the very fabric of space itself. This dazzling disclosure has ignited various conversations and explanations, with esteemed analysts and prominent observatories around the planet being constantly bombarded with ordinary questions about it. The most well-known of these questions is, how can the James Webb Space Telescope distinguish a 13.8 billion-year-old development when the universe is significantly younger than that? To sort out this mystery, let us set out on this journey with responsive viewpoints, tremendous interest, and a sense of wonder that transcends the constraints of our regular existence. Yet first, to grasp this puzzling construction, we surely need to look at this in the farthest reaches of the universe. Around 200 light-years away lives a regarded star known as HD 14283. This subgiant star, situated about 13.8 billion light-years from Earth in the heavenly body Libra, offers beguiling insights into its violent past. Around 13 billion years ago, this star wasn't extraordinary only because of its construction, but also because it is an anomaly in time. It existed when our Milky Way was still in its infancy, absorbing a dwarf galaxy that once called it home. Anyway, what really captivates our galactic interest in HD 14283 isn't just its rapid interaction, but its astonishing age. Among the heavenly components we have seen, it remains as maybe the most ancient star we have encountered, earning the enchanting name Methuselah star. Like the biblical figure Methuselah, who lived for 969 years, this star's age has dazzled cosmologists. Early estimates pegged its age at a shocking 16 billion years. However, the latest calculations using NASA's Hubble Space Telescope suggest a slightly more energetic age of 14.46 billion years, with a margin of error of 0.8 billion years. This revelation regarding its age flabbergasted stargazers as the age of the universe, based on measurements from the Cosmic Microwave Background (CMB), is thought to be around 13.8 billion years. This issue has raised huge questions concerning the star's age, the universe's age, and surprisingly, the accuracy of our dating techniques. The James Webb Space Telescope is an amazing achievement of human ingenuity that will change the way we explore space. Named after James E. Webb, a key figure in NASA's early days, this superpowered observatory is taking our space insights to an unfathomable level. Designed to detect infrared light, it can capture signals from the farthest and oldest objects in the universe, offering a clearer view of the universe's origins. Now, before we explore the captivating details of how the James Webb Space Telescope detected the 13.8 billion-year-old development, we must ensure we're on the same page regarding the age of not just the universe but also celestial objects. Determining the age of celestial objects can be a perplexing enigma. For example, consider stars. They are as ageless as light, maintaining their brilliance, temperature, and size for billions of years, making them difficult to date. Cosmologists use variations in brightness and color as indicators of their age, comparing these observations to models predicting how stars evolve over time. One clue to a star's age is its rotational speed. Just as a wheel slows down due to friction, stars also decelerate as they age. What clue does the Milky Way provide for the age of this intriguing star as we continue our journey for astronomical knowledge? Let us now focus on the enchanting dance unfolding in our vast backyard. The Milky Way's latest assessments have uncovered a mesmerizing display. Stars on the outer edges of our galaxy show a more relaxed, almost slow movement compared to their counterparts in other galaxies. This discovery has sparked a cosmic investigation, prompting astronomers to explore the possibility that our Milky Way might be lacking a hidden massive component known as dark matter. Dark matter, a mysterious substance that eludes direct identification, exerts a gravitational effect on celestial objects, playing a puzzling role in the grand celestial dance. It presents an endless question that challenges our understanding. Maybe we have been approaching dark matter from the wrong angle. Enter the Gaia satellite, a celestial player from the European Space Agency, stepping onto the infinite stage and illuminating the complexities of nearly 2 billion stars within our Milky Way. Think of Gaia as an invaluable development instructor, providing precise measurements that encourage astronomers to rethink their cosmic choreography. At the edges of our Milky Way, stars appear to take on a more leisurely pace, challenging our previous assumptions about their speeds. The speed of stars can reveal fascinating insights into a galaxy's mass, much like evaluating the size of a crowd by observing how quickly people move. Armed with Gaia's meticulous data, cosmologists have approximated the combined mass of our galaxy's gas, dust, stars, and elusive dark matter to be around 200 billion times the mass of the Milky Way. However, Gaia's new data now suggests it is about half as much as previously estimated, which challenges our assumptions about the abundance of dark matter. This discovery leads to the hypothesis that our cosmic soup may contain fewer ingredients than previously thought. Measuring a galaxy, however, is akin to trying to measure the impossible. A challenging feat indeed. Gaia's data might have inconsistencies, or our cosmic measuring tape may require recalibration. Regardless, various research groups have joined the celestial investigation, all singing the same cosmic tune. If this astronomical discovery is confirmed, it will mark a new chapter in our understanding of galactic physics, a revolutionary shift in perspective, prompting us to reassess not just our Milky Way, but every shining corner of the universe. To fully appreciate the significance of this discovery, we must take a huge leap back in time. In the 1970s, astronomer Vera Rubin and her team set off to decipher the rhythmic patterns of stars and galaxies. The prevailing cosmic playbook suggested that stars on the outer edges of a galaxy would be sluggish compared to their zippy counterparts near the massive center, much like how Neptune leisurely orbits the Sun while Mercury races perilously fast. However, Rubin and her team uncovered a stunning surprise. Stars at the farthest reaches of galaxies were strutting their stuff at nearly the same speed as those closer to the galactic core. This galactic revelation implied the existence of a mysterious, unseen component, dark matter, the invisible heavyweight champion that envelopes galaxies in massive coronas. Now, let's focus on our cosmic backyard, the Milky Way. Imagine trying to track everything in your room while remaining inside. A ghostly endeavor indeed. Space scientists faced a similar challenge, assuming that stars in the Milky Way followed the same rules as those in other galaxies. For instance, our Sun, located about 26,600 light-years from the galactic center, orbits at a staggering speed of 800,000 kilometers per hour. In 2013, the Gaia satellite was launched, serving as a precise cosmic ruler, carefully measuring the positions and smooth movements of stars in our Milky Way in 3 dimensions. The data it has shared with us resembles a vast ensemble, refining its precision over time. In 2022, Gaia's latest data drop revealed subtle hints of cosmic deceleration. These subtle clues soon became monumental discoveries. The new data is twice as accurate as previous measurements from 2018, providing scientists with enhanced tools to track the movements of stars with laser precision, even across vast astronomical distances. In the Celestial Hall of 2023, free examination papers revealed a cosmic shock. Stars located up to a staggering 100,000 light-years from the center of the Milky Way seem to be slowing down. It's as though these stars have decided to cause a stir, enjoying a graceful dance reminiscent of the planetary waltz described by Johannes Kepler centuries earlier. In contrast, stars in other galaxies typically adhere to a similar rhythm, moving from the center to the outer edges of their massive homes without noticeable deceleration. This discovery has sparked a whirlwind of hypotheses and theories. One captivating possibility is that our understanding of dark matter may need an update. Dark matter is a hypothetical type of matter that doesn't interact with light or other electromagnetic radiation, making it invisible and challenging to detect directly. Its presence is inferred from its gravitational effects on visible matter. The prevailing model suggests that dark matter forms a vast, diffuse halo around galaxies, providing the extra gravitational pull necessary to explain the observed movements of stars and galaxies. However, if the stars on the outer edges of the Milky Way are indeed moving more slowly, it could suggest that the distribution or density of dark matter differs from previous expectations. This discovery has ignited discussions among scientists about alternative explanations and new avenues of inquiry. One possibility is that the change in stellar velocities could be attributed to variations in the distribution of ordinary matter, such as gas and dust within the galaxy. Alternatively, it could signal a new kind of physics, perhaps a previously unknown force that is influencing the motion of stars. Regardless of the interpretation, this research is just the beginning of a deeper exploration into the mysteries of the Milky Way and the universe beyond. As astronomers continue to analyze data from Gaia and other observatories, we can expect to uncover even more surprising revelations that could reshape our understanding of the cosmos. The study of galactic movements, dark matter, and the fundamental forces at work in the universe is a constantly evolving field, and each new discovery brings us closer to answering some of the most profound questions about our place in the cosmos as we venture deeper into the heart of these cosmic puzzles. One of the most intriguing aspects of modern astronomy is the interplay between galaxies, their dark matter halos, and the mysterious forces that shape them. The recent revelations about star movements in the Milky Way suggest that there may be hidden features of our galaxy's structure that we have yet to fully comprehend. While dark matter has long been considered the leading explanation for the gravitational effects we observe in galaxies, including the motions of stars, these new findings challenge the assumptions that underpin our models. If stars at the galaxy's outskirts are decelerating more than expected, this could imply that the distribution of mass within the galaxy is far more complex than originally thought. Additionally, there's the possibility that our current understanding of dark matter itself could be incomplete. Although it is known to interact gravitationally, it doesn't emit, absorb, or reflect light, making it nearly impossible to detect directly with current technologies. This invisibility has led scientists to hypothesize that dark matter forms a vast, spherical halo around galaxies, exerting its gravitational pull on visible matter. However, the unexpected movement of stars could suggest that dark matter is not uniformly distributed, or perhaps that there is some form of matter or energy in play that we haven't yet detected. Astronomers are also considering whether our fundamental theories of gravity and space-time need to be adjusted. Einstein's general theory of relativity has been a cornerstone of modern physics, and it has passed every test so far. Yet, as we delve deeper into the behavior of galaxies, especially those at great distances, there may be subtle deviations from expected predictions that suggest new physics. The motion of distant stars, the behavior of galaxy clusters, and the way that light bends as it passes through these cosmic structures could provide clues that help us refine or even overhaul our understanding of gravity. Another exciting avenue of research is the role that supermassive black holes play in shaping the dynamics of galaxies. These behemoths, found at the centers of most galaxies, are thought to influence star formation and galaxy evolution. Their powerful gravitational fields and the energy they emit can have far-reaching effects on their surroundings, potentially affecting the distribution of stars and dark matter in ways that we are only beginning to grasp. Studying the interaction between supermassive black holes and their host galaxies could unlock a whole new chapter in our understanding of galactic formation and evolution. On a more speculative note, some scientists are even beginning to entertain the possibility of alternative theories of gravity. Modifications to Einstein's laws, such as the concept of modified gravity or MOND, modified Newtonian dynamics, suggest that gravity behaves differently at the scale of galaxies than what we observe on Earth or in the solar system. These ideas are still far from proven, but they offer an intriguing possibility for explaining the cosmic anomalies that have puzzled astronomers for decades. As technology advances, so too does our ability to observe and understand these distant phenomena. The James Webb Space Telescope, with its cutting-edge infrared capabilities, will continue to reveal new details about the most distant reaches of the universe. As we peer further back in time and space, we may one day answer some of the most fundamental questions about the cosmos. Questions about the origins of galaxies, the nature of dark matter and dark energy, and even the very fabric of reality itself. As our observational tools improve, the potential for groundbreaking discoveries expands. The future of space exploration lies not only in observing distant stars and galaxies, but also in understanding the more subtle aspects of the universe's workings. One promising frontier is the study of gravitational waves, ripples in spacetime caused by massive objects like colliding black holes or neutron stars. These waves, first directly detected in 2015, have opened an entirely new way of observing the cosmos. Unlike traditional telescopes, which rely on light, gravitational wave detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, can provide insights into phenomena that are invisible to electromagnetic radiation. This could lead to new discoveries about the structure of the universe, including the dynamics of dark matter and the interactions between galaxies. Additionally, the role of exoplanets, planets orbiting stars outside our solar system, continues to captivate astronomers. Thousands of exoplanets have been discovered, with some situated in their star's habitable zone, potentially capable of supporting life. The upcoming missions, such as the European Space Agency's Aerial Telescope and NASA's LUVOIR, Large UV/Optical/IR Surveyor Telescope, are designed to analyze the atmospheres of these planets in unprecedented detail. These studies could eventually answer one of humanity's most profound questions. Are we alone in the universe? The possibilities for discovery are boundless, and we are only just beginning to scratch the surface of what the cosmos has to offer.